We want to now look at the various theories and approaches to solving fatigue problems. There are three major fatigue life models, and these are the methods that predict the life in number of cycles to failure for specific loading. And the three life models, fatigue life models, are the stress life method, the strain life method, and the linear elastic fracture mechanics method. And I'll expect you to be able to identify the three and talk about them a little bit. The stress life method is the one that we are going to use in this class. It's the least accurate, but it gives very good results based on the complexity of the model. It's the most traditional and by far the easiest to implement. So even though the first item is least accurate, and particularly for low cycle applications, it is still accurate enough to get good evaluations of the fatigue life. It estimates the life to fracture, but does not account for crack nucleation and crack growth. And it's based on comparison to experimental test specimens. And it's mainly based on the idea of what we will call the RR Moore beam. The strain life method is a more detailed analysis of plastic deformation at localized regions. And several idealizations are compounded, leading to uncertainties in the results. The strain life method is used when better answers or better results are needed than with the stress life method, but a full linear elastic fracture mechanics method is not required. However, to get a good result with the strain life method is a lot more challenging, and there's a lot more places where errors can be made. Then the last method, the linear elastic fracture mechanics method, it assumes a crack exists and then it predicts the crack growth with respect to what we call a stress intensity factor. And this is the most accurate method, but it is very mathematical and complex to apply to a practical problem. So we will focus again on the stress life method, which is based on the RR Moore beam approach. So what happened is Moore took a round rotating specimen and he measured how long it took to have the specimen fail in fatigue. So in this method, what Moore did is he took this beam and he polished this surface right here, and he carefully machined it to a very precise size. And then he put this in a spinning machine where he could apply a moment. And he applied a bending moment to this beam, and then as it spun, it would see tension and compression, and tension and compression, and then he would count the number of cycles till it failed. And what he did is he plotted this diagram where on the vertical axis here we plot what we call the fatigue strength SF, and on the horizontal axis we plot the number of cycles to failure. And so at 10 to the 0, this curve starts at the SUT, which makes sense. If this specimen were to undergo one cycle before it ruptured and broke, that would be the ultimate strength of the material. Then, as the number of cycles increases, you can see that the fatigue strength continues to drop. Now, the black dots here represent experimental data. And we can see that there's a pretty good linear relationship up to just under 10 to the 3rd cycles, and that there's a constant line, a constant slope. Then once we hit up in this region here, we have a steeper slope that comes down, and then here we actually go flat. So what this means is that if I were to give us this particular specimen a stress of 100, I could cycle it up to this many cycles before it failed in fatigue. Now for us in this class, we're going to make this chart a little bit easier to draw. We can see here that this inflection point occurs at a number less than 1,000. But we are going to make this number 1,000 for this class. And so between 0 and 1,000, we will go from the SUT down to this inflection point here. And then from 1,000 cycles up to 1,000,000 cycles, we will have this region here. And then above 1,000,000 cycles, we see that the SN diagram goes horizontal, which means that any stress in this region here, any stress below the endurance limit, will never cause a fatigue stress. And that's actually the definition of the endurance limit. This SE here is called the endurance limit, and it's the maximum stress that can be applied such that a fatigue failure will not occur. Then if the stress goes larger than the endurance limit, then we start to limit the number of cycles that our part can live for. Now you can see up here that we have finite life, and finite life is defined as being from 0 cycles, 1 cycle, up to 10 to the 7th. We're going to move this finite life back to 10 to the 6th, and then infinite life from 10 to the 6th on up. They give this region here because there's a lot of uncertainty when we get to this number of cycles. But we will use finite life from the first cycle up to 10 to the 6th, and then infinite life from 10 to the 6th up. Low cycle fatigue is often considered in this region here up to 1,000 cycles. And then high cycle is above 1,000 cycles. You'll note that the number of cycles to failure at varying stress levels is plotted on a log-log scale. So both axes here are on a log axis. For ferrous materials, a knee occurs here. The endurance limit occurs at 10 to the 6th. For non-ferrous materials, a lot of people say there is not an endurance limit. And we will discuss that in a minute. So you need to be able to reproduce this plot, label the important regions on the plot, and be able to discuss these important values. And again, this plot was developed when Moore took his beam and he finely machined it, carefully machined it to these dimensions, and then polished this surface to make sure there were no cracks. And then he spun it with an applied moment, and when it failed, he recorded the number of cycles and the stress and plotted this line. So we're going to look at this SN diagram again, but we're going to let this straight line region here, which we're going to say occurs at 10 to the 3rd cycles up to 10 to the 6th. This is the region we are most interested in fatigue analysis. In low cycle fatigue, there are other methods that are more accurate than the Moore beam approach and the stress life approach. And then if we have an endurance limit that is, if we have a stress that's lower than our endurance limit, we won't have a fatigue failure. So this region here becomes our critical region for design. The equation of this straight line right here is given by SF is equal to AN to the B. So this is the equation for a straight line in a log-log plot. Just like y equals mx plus b on a regular plot is the equation for a straight line, SF is equal to an to the b is the equation for the straight line on a log-log plot. So SF is equal to an to the b is the equation of this straight line. If I tell you the n, you should be able to come and compute the SF, which would then give me the associated SF over here. A and B are given by these two equations. A is equal to script F SUT squared over SE. The SUT is the ultimate strength of the material. SE is the endurance limit of the material. This F is called the fatigue strength factor and comes from this table here. So on this plot, what you do is you have script F on the vertical axis, and on the horizontal axis we have the SUT in KPSI. So if we know the SUT for our material, we come to the SUT and we come up till we hit the curve, and then we come over and we pick off our little f. Now you'll note that for most steels, the little f will be between 0.8 and 0.9 SUT, or the value for point F will be between 0.8 and 0.9. So coming back now to this equation for A, given our material, we would be able to look up F from the chart. We know our SUT and we know our SE. Then we could compute A. To get B, we have minus 1/3 the log of F SUT squared over SE. And you can see that the F SUT is this upper limit on the line, and SE is this lower limit on the line. So we could come over and mark this inflection point here as F SUT. And again, the F is typically between 0.8 and 0.9. And so given our material and our endurance limit, we could compute the fatigue strength associated with a number of cycles. You will use these equations a lot in our analysis. Let's now look at the SN diagrams for other non-ferrous materials. Here we have on the vertical axis the peak alternating bending stress, and then the number of cycles on the x-axis. And what happens is these would be wrought irons, some sandcast materials, and some permanent mold materials. And you can see here why people say that there's not an endurance limit. But on the other hand, I also argue that for these wrought materials, and certainly here in some of these other materials, this line starts to go pretty flat. The inflection point might not be 10 to the 6th like it was for ferrous steel, but coming out here to 10 to the 8th and some of these higher numbers, I would argue that we have a close approximation to an endurance limit. Takeaway points are non-ferrous metals often do not have an endurance limit. Fatigue strength SF is reported as a specific number of cycles. So in order to report SF, you need to have SF at 10 to the 5th cycles, or SF at 10 to the 4th cycles. And this figure above shows typical SN diagrams for various aluminum materials as well. In our fatigue analysis in this course, we will stick with the fatigue analysis of low carbon structural steel. We now want to look at a relationship between the ultimate strength and the endurance limit. And what we can see here is a bunch of experimental data where the ultimate strength was plotted on the x-axis and the endurance limit was plotted on the vertical axis. And you can see that the endurance limit here is called SE prime. And what we see is that the experimental data kind of follows this dashed line up to a point and then goes horizontal. And so what researchers have done is they've fit these data and they say that SE prime, the endurance limit, is equal to 50% of the SUT as if the SUT is less than or equal to 200 kpsi. Then if the SUT is greater than 200 kpsi, the SE prime is simply 100 kpsi. And it doesn't increase, it holds flat. So even though our ultimate strength continues to increase, the endurance limit doesn't increase. Now, this SE prime is what we are going to call the unmodified endurance limit. And so this is the case that you would have if you had a perfect RR Moore beam that was sized and polished and loaded carefully. So SE prime is the unmodified endurance limit. And we have a relationship as given here between the unmodified endurance limit and the SUT of the material. We'll use this equation a lot in our analysis, and it's important that you can visualize and remember this information. Now what we need to do is modify our endurance limit for the particular problem at hand. And this is where Chapter 8 or Chapter 6 will be very helpful to you. That's in creating a modified endurance limit. So the endurance limit SE prime is for carefully prepared and tested specimens that follow the guidelines of the RR Moore beam. In most applications, we cannot follow those conditions. We have different loads, we have different materials, different finishes, different load applications. The temperature may be different. And so we need to be able to modify our endurance limit. And so we do that by writing our endurance limit as shown here, where SE is equal to all these modification factors times SE prime. So SE prime is the unmodified endurance limit, and it's 50% of the ultimate strength up to 200 kpsi, and then it's 100 kpsi if the ultimate strength is greater than 200 kpsi. So now we're going to focus on computing these endurance limit modification factors. And these modification factors are often referred to as the Mar29 factors. So the little k's here represent the Mar29 factors. The first one, Ka, is associated with a surface condition factor. So this would be whether the material is ground, polished, or cold drawn or hot drawn. Kb is the size modification factor. Moore built his beam for a round rotating bar, and if we have a different geometry than that, we need to account for the size. Load, Kc is for the load modification factor. This is where if we have bending, torsion, and an axial load, how do we modify the endurance limit? The endurance limit is a strong function of temperature, and so we have a Mar29 factor specifically for the temperature. And Ke is a reliability factor based on the reliability we want to have in our model. And then K sub f is the miscellaneous effects modification factor. This one includes a bunch of stuff. For us, we will mainly focus it on stress concentration factor effects. And then SE prime is the rotary beam test specimen, the unmodified endurance limit, and SE is the endurance limit for the particular problem we're solving. Now what we're going to do is come and look at each one of these Marin factors individually and make sure we understand how to compute its value. Hello, and welcome to another video lecture for Machine Design ME372. In this video lecture, we are going to focus on computing the Marin factors, which are used to modify the endurance limit. We mentioned in the previous video that our modified endurance limit is called SE. Our unmodified endurance limit is SE prime, which is given by the equations here on the previous page. We now want to go through and compute these individual Marin factors. The first one that we will look at computing is called the surface factor. And this is associated with the surface finish of the part. Ka is computed by taking A SUT to the B, where A and B come from this table. So for example, if we have a ground surface finish and we're using kpsi units, then A is 1.34 and my exponent B is minus 0.085. Then I put my SUT in terms of kpsi. Make sure you don't put the SUT in terms of psi or pascals, but the SUT needs to come in here in terms of kpsi or MPAs, megapascals. One important thing to note about all the Marin factors back here on this page is that all of these values should be less than 1. We will see that for some temperature effects, the ideal temperature is actually a little bit warmer than room temperature, and we get a Marin factor that can be slightly greater than 1 for Kd. But that's only in a particular situation. And in general, all these Marin factors should be less than 1. So if you come over here and put in the wrong units and compute a very large Ka, you'll know that it is in error. So here's an example. It says a steel has a minimum ultimate strength of 520 MPas and a machined surface finish. Estimate Ka. So we would come up to our machined surface finish and we see that we're using units of MPas. So I put 4.51 in for A. SUT is the 520 and my exponent is minus 0.265. And so I compute my Ka and it turns out to be less than 1 and in the range that makes sense. A machined or cold drawn surface is usually a pretty good surface, and so we would expect a relatively high value here, or a value close to 1. That's the surface factor, Ka. Now we look for the size factor, Kb. And Kb deals with parts that have a larger surface area and likely a higher expectation for a crack to initiate. The size factor takes into account the geometry of the cross-section and whether the cross-section is rotating or not. The size factor is given the symbol Kb. And the way we compute Kb is we take the diameter of the rod, divide it by 0.3, and raise that quantity to the negative 0.107, and that computes KB. Now, this equation holds as long as my diameter is between 0.11 and 2 inches. If my diameter is greater than 2 inches, then I need to use this expression here. And these are the metric counterparts for these expressions. Now what typically happens is we have a part that is not round, and so that it doesn't have a diameter. And what we need to use here is what we call D effective, or the effective diameter. The next slide shows us how we compute this effective diameter. So for parts that are not round and rotating, an equivalent round rotating diameter is needed. What we do is we equate the volume of material stressed at and above 95% of the maximum stress to the same volume in the rotating beam specimen. The lengths cancel out, and so we can equate the areas. So for a round rotating section, the 95% stress area is the area of a ring. So if I have a bar that is circular and it's rotating, the area that sees 95% of the stress is given by this expression here, where I have d squared minus 0.95 d squared times by pi over 4. And this is 0.0766 d squared. So this is the area in the round rotating bar that carries 95% of the stress. It's a ring on the outside of the bar, and the ring area is given by 0.0766 d squared. Now what we do is we take the other geometries that we're interested in and we set them equal. We figure out what their 95% stress area is, and we set that equal to this 95% stress area for the round rotating bar. So equate 95% stress area for other conditions to equation 622 and solve for D as the equivalent round rotating diameter. For a non-rotating round bar, we know that the A95 is 0.01046 d squared. So if we have a non-rotating round bar, the way that I would solve for the d that goes into the KB equations is to take this 0.01046 d squared and set it equal to the 0766 d squared. This d here becomes d effective, and I solve for d effective here, and I get d effective is equal to 0.370 d. So I'd stick in the diameter of my non-rotating round bar, and I would compute the effective diameter that I would then come back to these equations here for KB, and I would use D effective in these expressions to compute KB. Now your book has a nice table where it gives you the A95 for the particular cross-section and geometry, and it also gives you the D effective. I want to make sure that you understand the process of computing D effective. So on a quiz or on an exam, I am going to have you actually compute these D effective values. And again, you do that by setting the A95 of the part equal to the A95 of a round rotating section, and we solve for the D of the round rotating section, and that becomes D effective. you should be able to take this A95 and compute this D effective for these other geometries. As an example, let's compute a KB. Here it says a steel shaft loaded in bending is 32 millimeters in diameter. It's abutting a filleted shoulder 38 millimeters in diameter. The shaft material has a mean ultimate tensile strength of 690 MPa. Estimate the Marin size factor, KB, if the shaft is used in rotating mode and non-rotating mode. So first of all, if we're doing rotating, we come back to our equations and we see that the 32 millimeters falls in this region. And so I'd simply take the 32 divided by 7.62 and raise that to the minus 0.107 and get my KB value. And that is what has been done here. And I get a KB of 0.858. Then if we have a non-rotating mode, I have to compute D effective. And I can look up D effective in the previous table, and I can compute D effective, and it turns out to be 11.84. Then I take that 11.84 and stick it back into the KB equations, and I get a 0.954 for a KB. Now, one other very important thing to note about KB is that for axial loads, so if the member is seeing an axial load, there is no size effect, and KB is equal to 1. Make sure you don't forget that, because you could be given a complicated system where it would be a challenge to compute KB, but then if your loads are all axial, there is no size effect, and KB is simply equal to 1. KB is one of the harder ones to compute. Make sure that you review these slides and get any questions you have with computing KB answered. The next factor is KC, which is a loading factor. You only use KC if a single load is applied. So if we only have bending, or we only have an axial load, or we only have torsion, then we apply KC as shown here. If, however, we have bending and axial, we let KC equal 1, and we address KC in another equation. So, in combined loadings, you need to compute a von Mises stress. And recall that you can use the Marin factors to decrease the strength or increase the stress when using the von Mises equation. So we have these cases. Nothing needs to be done to the bending stress, Kc equals 1, if you have a case of pure bending. The axial stress needs to be divided by Kc equals 0.85, or we multiply our Marin factor, Kc, by the Se. The torsional stress is already accounted for in the equation. We'll look at an example problem of this later on. For now, remember this table for single load types. So if you have pure bending, Kc is 1, pure axial load, it's 0.85, pure torsion, it's 0.59. Kc is very easy to apply. The next modification factor is the temperature factor, Kd. And this is a simple lookup value. What we do is we simply look up the temperature that our system will be operating at, and we come and we pull off the Kd value. Kd is equal to St over Srt. So this is the column of Kd values. And you can see here that at room temperature we have a Kd of 1. And that's where Moore did his testing. if we have elevated temperatures, you can see that KD becomes slightly greater than 1. However, I would never use a value greater than 1, and I would encourage you to do the same. Then you see that as the temperature gets up to 300 C and higher, the KD factor starts to become significant. You need to be careful not to double count KD, so don't modify the ultimate strength for temperature and also use a KD value, because that would be double counting for KD and temperature effects. If the rotating beam endurance limit, SE prime limit, is known at room temperature, then use KD from the table above to correct it. If SE prime is not known, compute it using the temperature adjusted SUT. The SUT temperature modifying factor is also given in the table above. Note that changing the SUT changes other Marin factors as well. So it's better to modify the SUT based on the temperature than to simply adjust for it here. And that's because a modified SUT will change other Marin factor values. This is an important note that you will need to make sure you remember on homework and on an exam. If you can modify the ultimate strength for temperature, do it, because it will modify other Marin factors. If you can't, then this is kind of a last-ditch effort to approximate the temperature effects. We can look at a couple examples of computing KD. So in this first example, it says a 1035 steel has a tensile strength of 70 and is to be used for a part that sees 450F in service. Estimate the Marin temperature modification factor and SE. If the room temperature endurance limit by test is 39 and B, only the tensile strength at room temperature is known. So from equation 627, we can compute KD, and KD turns out to be 1.007. Thus, to modify the endurance limit at 450, we simply go to 1.007 and multiply that by the 39 to get 39.3 kpsi. Now, interpolating from table 6.4 gives us this expression here where we get 1.007. Same way we could have computed it up here. The interpolation essentially does the same thing. So the tensile strength at 450 is estimated to be given by this expression here, which gives us 70.5 kpsi. Then from equation 6.8, the endurance limit becomes 0.5 times SUT 450, which gives us 35.2 kpsi. Part A gives the better estimate due to actual testing of the particular material, but make sure you see the two different approaches to solving this problem. The next factor that we want to talk about is the temperature factor, KD. This temperature factor is quite easy to apply, but care needs to be taken when doing so. The basic idea is to look down the temperature column, then come over and get ST over SRT, which represents the KD value. You can see that at 20 degrees C, room temperature, we have a KD of 1. And then as the temperature increases up to around 200 C, we actually have an increase in the KD value, and this is the only KD value that should ever be greater than 1. And like mentioned before, I would still just use a KD value of 1. You can see as the temperature continues to increase, we have quite a rapid drop-off in the KD value. Now, we need to be careful not to double count KD. You don't want to modify the ultimate strength due to temperature effects, and use KD. If the rotating beam endurance factor, SE prime, is known at room temperature, then we'll use the KD from the table above to correct it. If SE prime is not known, compute it using the temperature adjusted SUT. The SUT temperature modifying factor is also given in the table above. And note that changing the SUT changes other Marin factors as well. So if temperature is the only Marin factor that you need to adjust, Ka, Kb, Kc, and all other Marin factors are 1s, then it is usually best to apply Kd to the uncorrected SUT. However, if you have other Marin factors that are not 1, like there's a Ka, Kb, and Kc, and so forth, then you need to correct the ultimate strength for temperature, because temperature will affect those other Marin factors, and it would not be sufficient to just use Kd. So again, if temperature is the only concern and all other Marin factors are 1, go ahead and use Kd in the equation to compute SE. However, if there are other Marin factors that are not 1s, then it's best to modify the ultimate strength for temperature, and then so that we don't double count, Kc would enter the SE computation as a 1. Let's look at an example problem. So here we have a 1035 steel, has a tensile strength of 70, and it's to be used for a part that sees 450 F. Estimate the temperature modification factor and SE at 450. If the room temperature endurance limit by test is 39, so that's SE prime is 39, and B, only the tensile strength at room temperature is known. So in this case, to do part A, we can compute Kd using this expression that's given as equation 627 in your book, or we can use interpolation and come up with this expression, or this number using interpolation, as we'll do in the next part of the example. So in this case, we know the room temperature endurance limit by test is given as SE prime at 70 degrees as this, and the only thing we want to do is modify it for temperature. Then I'm just fine to come here and use Kd and compute 39.3. Now, if only the tensile strength at room temperature is known, then I need to come down here, and my SUT at 450, I can modify my SUT. And here I modify my SUT by ST over SRT, and I get 1.007 times the 70 to give me 70.5. And then from equation 8, I can get SE at 450 by 0.5 times SUT at 450. And that would give me 35.2. Note here, I don't compensate for Kd because I modified SUT for temperature. Now, in this particular case, because there aren't any other Marin factors considered, Part A gives the better estimate due to actual testing of the particular material. But given that other Marin factors are involved, then you need to modify the ultimate strength for temperature and compute all those other Marin factors based off of the modified ultimate strength. So be careful with this statement here. In this particular case, Part A gives a better estimate due to actual testing, But that's because this is the only Marin factor that we are considering. The next Marin factor is the reliability factor, Ke. And Ke accounts for uncertainty on the endurance limit. It does not take into account uncertainty on any other terms. It's only on the endurance limit. So values for Ke are given in this table below. If we want a 50% reliability, then we use Ke as 1.0. So this is the default, a 50% reliability, which is not very good. But you can see that we go from a 50% reliability to a 90% reliability simply by dropping from a 1.0 to a 0.897. And then 95 and 99% reliability have additional drops. To get to a 99.49's reliability, you have a very large reduction due to your Ke. So this is the Ke that modifies the endurance limit simply based on the reliability that you want to have. And again, this doesn't account for reliabilities or uncertainties on ultimate strengths and uncertainties on loads and forces and geometry. All this is the uncertainty associated with the endurance limit quantity.